Okay, so like I said, I did get your homework graded from last night, and by and large, it looks like people did really good. Probably the most consistent thing I commented on was that a couple people, I think one or two, not very many, just wrote on the normal ABG, they wrote like normal acidosis or whatever. But if everything's normal, it's just a normal ABG. Even if the pH happens to be in the acid normal or base normal range, if both the CO2 and bicarb are normal, that just makes it a normal ABG. Yeah. But other than that, it looks like you guys did really well, and I'm really impressed with the compensation that you were able to pick up on partially and fully compensated and uncompensated fairly quickly and fairly easily. So as we started working on the case studies or the exercise this morning, we started talking a little more about oxygen. We completely neglected oxygen for the most part yesterday, and we focused primarily on acid-base balance. So I do want to spend a few minutes talking about oxygen transport and measuring the amount of oxygen in the body, because that is something important, that is important information that the ABG gives us. So the ABG kind of gives us a few different things. First of all, it's used to determine acid-base balance and helps us identify acid-base imbalances or problems with acid-base. The second is it gives us some idea of how well our patient is oxygenating. And then the third major thing that the ABG does is it allows us to identify abnormal forms of hemoglobin. And we talked about this during pharmacology. There was, during the toxicological drugs, we talked about abnormal forms of hemoglobin like methemoglobinemia, carboxyhemoglobin, right, when carbon monoxide attaches to hemoglobin. Cyanohemoglobin can sometimes happen when cyanide attaches to hemoglobin, although cyanide prefers other iron-based proteins in the body. But be that as it may, there are all these different abnormal forms of hemoglobin that can form. Your standard ABG actually cannot identify abnormal hemoglobin. So your standard ABG is going to give you your pH, your CO2, your PaCO2, your PaO2, your bicarb, something called the base excess, base deficit, and we may get into that a little later on. But it won't actually tell you abnormal hemoglobin. So if you suspect that there is an abnormal form of hemoglobin, you need to run or you need to get a special kind of ABG ordered, and that is known as co-oximetry. So co-oximetry looks at multiple wavelengths of light, and those multiple wavelengths of light can be used to determine if abnormal forms of hemoglobin are present, because these abnormal forms of hemoglobin will emit and absorb slightly different wavelengths of light, whereas your ABG uses a fairly limited number of wavelengths to make some of its measurements, particularly when it comes to looking at the saturation of hemoglobin. It's one of the reasons why pulse oximetry, for example, pulse oximetry is not good at identifying abnormal forms of hemoglobin. If somebody, say, has carbon monoxide toxicity, pulse oximetry, because it uses a limited number of wavelengths of light, can't tell the difference between oxyhemoglobin and carboxyhemoglobin, right? So hemoglobin that has oxygen bound to it, hemoglobin that has carbon monoxide bound to it, they absorb the wavelengths of light that pulse oximetry uses. They pretty much absorb at those same wavelengths, so you can't tell. So with co-oximetry, you can actually use multiple wavelengths, and you can actually tell, oh, this person has 50% carboxyhemoglobin, or whatever the case may be. So you got your standard ABG, and then you've got your co-oximetry. So I wanted to have a brief conversation about oxygen transport, and we're going to review these concepts, or we will return to these concepts again in the respiratory and pulmonology block of instruction during the paramedic pipeline, but this kind of builds that groundwork. All right, so these are the three major values that we're going to run into, the PaO2, the SaO2, and the SpO2. Now, some people will falsely use the SaO2 and the SpO2 interchangeably because in normal patients with normal physiology, there's not going to be a whole lot of difference between the SaO2 and the SpO2, but they are obtained very differently. So remind me, what does a little a mean? Arterial. So this is a saturation of arterial oxygen. This is a partial pressure of arterial oxygen. And the SpO2 is what comes from a pulse oximeter, not an ABG analysis. And the SpO2 is capillary, right? It is actually measuring the saturation of oxygen within your capillary beds. And if you have a very sick patient, particularly, the SpO2 values may be very different from the SaO2 values, particularly if someone is shunting or they're not perfusing their periphery and their peripheral capillary beds aren't being perfused, or they're hypothermic. The SpO2 value may be very different from the SaO2 value. Does that kind of make sense there? So we can't use them interchangeably in many situations other than a healthy person who is normal body temperature and doesn't have significant shunting of blood from their periphery. Okay, so we talked about carbon dioxide transport. We said that carbon dioxide is a fairly linear molecule, it's fairly polar, and it's not particularly soluble in water, right? And so for the most part, carbon dioxide had to be transformed into something that could be dissolved in water. Does that make sense? And that thing is carbonic acids. So about 70-75% of all the carbon dioxide in your body gets converted to carbonic acid. Some of it gets dissolved as a gas, and then some of it can actually attach to hemoglobin as well. Oxygen, if you think about oxygen, do you think oxygen is a polar or nonpolar molecule? Actually, oxygen is more polar than carbon dioxide, right? When you have two of the same atom, right, covalently bonding, right? So two oxygen atoms are bonding to form an oxygen molecule. Well, those oxygens have exactly the same electronegativity, which means what? There's equal sharing of the electron density, right? So it is a highly polar molecule. It's less likely to dissolve in water than carbon dioxide is under normal circumstances. And so it is even more critical that the body has some mechanism for transporting the oxygen. Now, in the case of oxygen, we don't tend to convert oxygen into some intermediate molecule. So what happens is oxygen gets transported in an unchanged form. And so we actually have a special protein, well, a couple of special proteins that can transport oxygen. The one that you're probably most familiar with is something called hemoglobin, right? And where does hemoglobin exist? Primarily within red blood cells, right? You also have a protein that is very similar to hemoglobin called myoglobin. Has anyone ever heard of myoglobin? You probably heard of it when you learned about something called rhabdomyolysis and breakdown of tissues and the release of myoglobin, and that free myoglobin in the blood is pretty rough on the kidneys, and that's all part of something called rhabdomyolysis. But where is myoglobin primarily located? Primarily located in your muscles, and it is the myoglobin that actually allows your muscles to endure low perfusion states. So, for example, when I go and run, right, my muscles are going to be using an incredible amount of energy, right? They're going to be making a lot of ATP. They're going to require a lot of oxygen in order to make that ATP for them to work out. And what might happen? Those muscles might not get enough perfusion, right? And so what those muscles have is they have not circulating in the blood, but embedded within the muscle cells themselves, we have these myoglobin proteins, and these myoglobin proteins, oxygen binds to them, And then when the muscles do not get oxygen, when they're in a hypoxic state, the oxygen gets released from the myoglobin within the muscles, and that allows them to tolerate these anaerobic states much better than most tissues in your body, right? Your neurons, for example, cells within your brain, do not have myoglobin, do not tolerate low perfusion states, do not tolerate low oxygen levels. In fact, they are some of the most sensitive cells to oxygen, whereas muscle is very, or skeletal muscle at least, is very good at compensating for this for sometimes prolonged periods of time. Okay. So let's talk about hemoglobin. So here I have a red blood cell, and this is where most of the hemoglobin is located. The hemoglobin is a quaternary protein. Remember, we talked about protein structure earlier on in this course during the chemistry block, and we said that proteins are the result of long chains of amino acids, and then the R groups begin to interact, and the protein begins to fold, and you get different levels of structure: the primary structure and the peptide bonds. The secondary and tertiary structures tend to be the intermolecular forces, the hydrogen bonds, the van der Waals forces, the induced dipoles, all of those interaction with the R groups. And then you can get these globulins that develop, and then those individual globulins can actually come together, and sometimes even other things like metals get drawn into the mix to form what's known as a quaternary structure. Hemoglobin is a quaternary structure protein, and it actually has 4 different globulins, two alpha globulins and 2 beta globulins. They're slightly different, but essentially the same, and those 4 globulins come together to form a molecule of hemoglobin. And so each of these globulins at their heart contain what's known as a porphyrin ring. And essentially what that porphyrin ring is an iron. We talked about this in pharmacology, right? You have an iron atom, and that iron atom is surrounded by nitrogens, and then kind of held down at the bottom in place by an amino acid residue. And the only part of that iron that's kind of open and free to interact is kind of the top part there, right? And the iron is in a +2 state, right? So it has 2 electrons that have been taken away from it, so it is positively charged, which means it tends to attract electrons, right? And remember, yesterday we talked about how electrons like to pair up. And so when we look at a molecule of oxygen, all right, that's 2 oxygen atoms double covalently bound to each other, and then we have these pairs of electrons, valence electrons, something kind of like that. And so what happens is these pairs of electrons become attracted to the iron in its +2 state, right? And so these valence electrons are attracted to that iron in the hemoglobin, and that's actually what holds the oxygen in place. Does that make sense? All right. So what happens is oxygen has to be transported. It can't dissolve in blood very efficiently, but oxygen can attach to the hemoglobin, and then that hemoglobin will then transport the oxygen to where it needs to go. You guys okay with that? So I think a good question that comes up from this is, well, what is going on with oxygen? What makes oxygen bind to hemoglobin in the first place? And once oxygen gets bound, right, well, what would make oxygen decouple from the hemoglobin, right? I get it that the iron is positively charged and the valence electrons of the oxygen are attracted to that, but why would the oxygen want to leave the hemoglobin once it gets attached? Once why?
I think it's pH and heat.
Yeah, something has to happen, and this is actually, it's pretty amazing when you think about it. So what I want to do is I want to talk about at the tissue level. So let's just assume for the moment, let's just assume some hand-wavy magic, and we'll come back to that, right? I don't like magic and hand-waving, so we'll knock the hands aside and actually explain it. But let's just assume right now that we have a fully oxygenated hemoglobin molecule, all right? And obviously we have many of these within the red blood cell, but we're just going to simplify. So I have a molecule of hemoglobin, and it has 4 oxygen atoms attached to it. You guys good with that? And then this red blood cell is circulating through, and this red blood cell is now in the capillaries, and the capillaries are interfacing with tissues. So here I have the tissue bed, and what are the tissues doing? Well, the tissues have cells within them that are doing metabolism, right? All sorts of metabolic processes, and they need ATP for that, right? So what are the cells doing? Well, remember energy production in eukaryotic cells. Glucose comes in, it enters glycolysis, gets turned into pyruvate. Pyruvate enters a Krebs cycle. Carbon dioxide comes out of the Krebs cycle as a waste, right? And then NAD and FAD transport hydrogen ions and electrons into the electron transport, right? And that's where actually most of the ATP is produced in electron transport. And then oxygen needs to come in as an electron acceptor to kind of act as a garbage truck in a sense, right? To get rid of the hydrogen ions and the electrons after they've been used to facilitate making ATP, right? So CO2 is coming out of the Krebs cycle, oxygen is going into the electron transport where a protein called ATP synthase is making, but there's another protein next to it that is actually using the oxygen to get rid of the wastes, quote unquote, that are coming out of electron transport. Okay, makes sense, right? So far so good. All right, so what happens is as this red blood cell moves through, it encounters lots of carbon dioxide that's being produced, right? These cells, right, making energy, they're producing waste. Well, what happens with CO2? Can CO2 easily dissolve in the blood? No, we talked about that yesterday, right? Can CO2 go through cell membranes fairly easily? Yeah, because cell membranes are primarily lipid-based, right? The phospholipid bilayer that we've talked about. So the carbon dioxide diffuses through cell membranes very easily, and much of the carbon dioxide will diffuse into the red blood cell here. And then once inside of the red blood cell, what happens? Well, you have carbonic anhydrase, right? The enzyme that catalyzes CO2, the chemical reaction of carbon dioxide combining with water, right? CO2 combines with water to form what? Carbonic acid, right? And then carbonic acid breaks down into hydrogen ions and bicarbonate ions. So here's a hydrogen ion, here's a bicarbonate ion. You guys okay with that? So here's the interesting thing. Once that hydrogen ion is produced, some of those hydrogen ions will actually attach to hemoglobin. And when those hydrogen ions attach to hemoglobin, they do not attach to where hemoglobin is bound to oxygen. They attach to a secondary site. And do you guys remember in pharmacology, we talked about allosteric modification? By the looks on your faces, okay. So remember when we talked about benzodiazepines, right? And the mechanism of action of a benzodiazepine is that it interacts with the what? The Gaba receptor. And remember, the Gaba receptor is a chloride channel that allows chloride to enter the cell. Now, do benzodiazepines cause the GABA receptor to open up?
Yeah.
No,
Oh, wait. No.
they do not. Right? They do not bind to the active site of the GABA receptor, right? So they do not mimic the action of GABA. They bind to another site of the GABA receptor, and then remember what they do is once the GABA binds, the receptor stays open longer, right? So the benzodiazepines do not directly agonize but rather they modify its behavior in response to something else. That is what we mean by allosteric modification, right? So the hydrogen ion bonds with hemoglobin, and what it does is it changes the shape ever so slightly. And remember, we said that protein function is related to its shape, right? And its conformation. The conformation of the protein is what determines how it's functioning. So it changes the conformation ever so slightly, and that conformational change makes the hemoglobin have a low affinity for oxygen. The hemoglobin, because essentially what happens is that iron atom kind of gets pulled down a little bit, and it can't interact with the oxygen. So what happens to the oxygen? It pops off the hemoglobin, and because the oxygen is not soluble in water, it diffuses out of the red blood cell, right, where you have lots of oxygen, and into the tissues where you have less oxygen, right? Does that make sense? This is something known as the Bohr effect. The Bohr effect. The Bohr effect. The Bohr effect is when hemoglobin has a lowered affinity for oxygen in the presence of an acidotic state. So as red blood cells go into acidotic areas of the body, they are more likely to offload oxygen, and more than likely, the more acidotic parts of your body are parts of your body that need the oxygen, right? Because there's more metabolism going on there. Does that make sense? That's called the Bohr effect. And then what happens is when this red blood cell gets into the pulmonary circulation, the pulmonary capillaries, well, what happens? Well, that hydrogen pops off of the hemoglobin. It combines with bicarbonate to form carbonic acid, which then breaks down into carbon dioxide and water, and the carbon dioxide leaves, right? And it gets exhaled. And so now the hydrogen pops off of the hemoglobin, and what happens? The iron pops up a little bit, and now the hemoglobin has a high affinity for oxygen, and what happens? Oxygen attaches. Does that make sense? That is something known as the Haldane effect. The Haldane effect. So the Bohr effect is when hemoglobin has a decreased affinity for oxygen in acidotic areas of the body, and the Haldane effect is where hemoglobin has an increased affinity for oxygen in more alkalotic areas of the body. And this is a primary or a very important mechanism that regulates the delivery and transport of oxygen by hemoglobin. Does that make sense? Furthermore, acid-base imbalances can impact the affinity that hemoglobin has for oxygen, right? If I make your entire body acidotic, right? So all of your blood plasma is very acidotic. You have some sort of acidosis. What is that going to do to the hemoglobin? Good. It is going to lower the affinity that hemoglobin has for oxygen. And even in the lungs, the hemoglobin is going to be less likely to bind as much oxygen, right? So acidosis causes a lowered affinity for oxygen. And likewise, if I make somebody very alkalotic, what might that do?
Higher affinity.
Right. So what will happen is the hemoglobin will have a higher affinity for oxygen, which means that it will be less likely to offload the oxygen where it needs to go. Does that make sense? You guys okay with that?
So is that where you get those spiked values of like the PaO2, where you're like 200?
So those, on those little case studies, and we'll talk about that a little more, those are more than likely the result of the respiratory compensation, right? So someone has, say, a metabolic acidosis, they're going to compensate by increasing, right, their depth and rate of breathing, and that tends to just cause hyperoxygen. And then if you put somebody on supplemental oxygen, then their oxygen levels are going to go up even higher. So in a lot of those cases, those are simply due to the compensatory process and often due to us, just adding supplemental oxygen into the mix. But this gives rise to another concept. And I don't want to go into great detail because we are going to hit it again in pulmonary medicine, but it is a concept known as the oxyhemoglobin dissociation curve. And the oxyhemoglobin dissociation curve is just a graph. And it's SaO2, right? So you graph SaO2 is a function of PaO2, right? And SaO2 goes from 0 to 100%. You guys okay with that? And here at 50. And then PaO2 is 0 millimeters of mercury all the way up to, as high as you want to go, right? You could go very high. If you put somebody in a hyperbaric chamber, you could go into the thousands. But we'll just cut this off at, say, 500 millimeters of mercury, because that would be about as high as you could get at atmospheric pressure if you put somebody, let's say, on a non-rebreather, something like that. It'd be really hard to get higher than that. And then right around here, so this would be 250. All right. There we go. All right, so right around here is where we would get. All right. And I won't even do that. Okay, so what happens is we can graph this and we can say at what PaO2 do I have a certain SaO2, right? And when I graph that, it's going to look something like this. All right, it's what's called a sigmoid curve, and sigmoid is just kind of like an S shape. So right down here, we see that hemoglobin has a low affinity for oxygen, right? So my saturation is very low and my PaO2 is very low. And then what happens is, as more oxygen binds to hemoglobin, what happens to its affinity? It increases, right? So if you have hemoglobin with no oxygen bound, it has a pretty low affinity. And then once the first molecule of oxygen binds, the affinity pops up suddenly. And then the second molecule binds and it gets even higher. Once more, the third, even more. And then what happens once the fourth molecule binds? It levels out, right? And can this go any higher? No, because hemoglobin, once it's fully saturated, right? Does that make sense? So this would be an example of, say, a normal affinity. And then what can happen is you can shift the affinity one direction or the other, right? So one way that I can shift the affinity, and let me just color code this, is if this shifts to the right. If this curve shifts to the right, all right? So this green color here is what's called a right shift. So what does that mean? Does hemoglobin, if it's shifted right, does it have an increased or decreased affinity? Decreased. It has a decreased affinity, right? So a right shift is a decreased affinity. And I just think of a right shift as releasing oxygen. Hemoglobin releases oxygen. Release O2, low affinity. And what kinds of things can cause a low affinity? Well, I just think of some R's. The first thing I think of, raised acids. Right, so acidosis is really good at causing this. Does that make sense? Raised acids, raised body temperature. So fever can cause this. A molecule called 2,3-diphosphoglycerate or 2,3 DPG, and for at this point, just think of 2,3 DPG as like a little crowbar. It kind of pops oxygen off of the hemoglobin. Certain patients, like COPD patients, can make lots of this. Right? So raised acids, raised temperature, 2,3, raised 2,3 DPG. Okay? And then likewise, we can have the curve shift this way. And this is what we call a left shift. All right. And so what's happening here? Does it have an increased or decreased affinity for oxygen? Right, so left shift is an increased affinity for oxygen. All right. And I think of the L's. So I think of low acid or alkalosis. Low acids or alkalosis will cause a left shift, right? I think of low body temperature. I think of low 2,3 DPG. And I think of lots of CO. Carbon monoxide tends to induce a very strong left shift. So if you have somebody who is poisoned with carbon monoxide, whatever oxygen you have attached to hemoglobin is not as likely to get delivered to the tissues. So this is a concept known as the oxyhemoglobin dissociation curve. And different conditions can shift the curve one way or the other, right? So if you make somebody or somebody becomes acidotic or alkalotic, right, they have a substantial acid-base balance. That acid-base balance not only can impact other processes in the body, but it can actually impact the way in which the body can transport and deliver oxygen to the tissues, right?
It's called one more time.
This is known as the oxyhemoglobin dissociation curve.
Dissociation?
Dissociation, yeah. So the oxyhemoglobin dissociation curve. And the black line is kind of a normal affinity, right? And then the red line is a high affinity or a left shift because when you graph it, it's to the left of the normal affinity. The green line's a right shift because when you graph it, you can see it graphs to the right of the normal affinity. Right? Left shift, high affinity; right shift, low affinity. Right? So I think of left shift as locking onto oxygen, right shift as releasing oxygen. And then you think of the R's for the right shift and the L's for the left shift. Does that kind of make sense there? You guys okay with that? Cool. All right. Excellent. Now, another thing that occurs, I want you to just put this in the back of your mind. As this, because remember, the hydrogen ions are kind of interacting with the hemoglobin after the carbonic acid dissociates, or some of the hydrogen ions. All right. And what happens is the bicarbonate tends to leave the red blood cell. So the bicarbonate will leave the blood cell and go into the bloodstream. And there's a very important concept that we're going to talk about, and it's going to be incredibly important a little later on today when we talk about more advanced concepts. And this concept is known as electroneutrality, right? That is to say that in the human body, there needs to be a positive charge for every negative charge, right? There needs to be a positive charge for every negative charge. The charge needs to balance out. That's known as electroneutrality. So if I have a negative charge leaving the red blood cell, what needs to happen?
Positive charge.
No. So if I have one negative charge, so the bicarb, I've got bicarb leaving the red blood cell. What might need to go into the red blood cell to replace that, to maintain electroneutrality?
Hydrogen.
Not hydrogen, but
Phosphate.
no, something else negatively charged, right? And what's probably one of the most common negatively charged ions we see in the body? Chloride, right? Right, because chloride tends to hang out with sodium, right? And so this is something known as the chloride shift. Chloride tends to shift in and out of the red blood cell as hydrogen and bicarbonate ions are shifting in and out, right, to maintain electroneutrality. The chloride shift is also referred to as the hamburger effect. No joke. It's actually the last name of one of the scientists that developed this. I forget the first name, but his last name was Hamburger. So the chloride shift or the hamburger effect. Okay, so you guys good with that? With oxygen transport? So the way that we can assess oxygen transport with the ABG is by the PaO2, right? And so that's the amount of oxygen that's actually dissolved in the blood, right, as a pressure. And then the SaO2 and SpO2 are looking at oxygen that's bound to hemoglobin, right? So those are the two ways we can transport oxygen, dissolved and bound, right? And we talked about the mechanism of oxygen transport and the affinity that hemoglobin can have for oxygen, depending on the situation. Okay. What time have we got? All right, we'll keep going. So now what I want to do is I want to take a deeper dive into these acid-base problems. And I'm going to start at some more of the straightforward problems. And these are going to be the respiratory problems. We're going to talk about the respiratory problems and then we'll move on to the metabolic problems. And metabolic problems are a lot more complicated and a lot more nuanced and a little difficult. So let's talk about respiratory alkalosis and respiratory acidosis. All right. So with respiratory alkalosis, what in general is happening? Like what's the general problem with respiratory alkalosis?
You're not retaining enough CO2.
Good. So you are getting rid of too much CO2, right? Right. So you are eliminating excessive amounts of CO2. And remember, CO2 can be roughly viewed as an acid, right? Because carbon dioxide gets converted to an acid via the mechanisms that we've already talked about. Right, so with respiratory alkalosis, you're eliminating excessive amounts of carbon dioxide. So what are some causes, if you had to think about it? Could you guys give me some common causes, some common pathophysiologies that can lead to respiratory alkalosis?
Panic attack.
Huh? Okay, so anxiety. Anxiety or panic, absolutely. What else? COPD? Absolutely, this is a common cause of respiratory alkalosis. This is an iatrogenic cause, right? Iatrogenic means healthcare provider caused, right? So this is provider caused excessive ventilation, right? Absolutely, that's a big one. What are some other things that can cause respiratory alkalosis?
Is that like when you start getting like altitude sickness or
Maybe.
pain?
Pain is a big one, yeah, pain, yeah. Pain. What about fever? What do you guys think there? Pain, fever, yeah. Believe it or not, early in an asthma attack, this happens too, right? So acute asthma. So early on during an asthma attack, we tend to hyperventilate, and your patient will actually be oxygenating very well, and they may very well have a low carbon dioxide level. And then what happens is, as they start retaining air, right, as the asthma becomes more and more obstructive and they start retaining more and more CO2, then they will go on to develop another deficit, another problem. Another reason that somebody can develop respiratory alkalosis is as a compensatory mechanism for metabolic acidosis. Compensating for a metabolic acidosis. Right. This is pretty common. This is actually very common. So, these are some of the things you want to think about if you identify respiratory alkalosis, right? These are the things you want to think about. Is this patient having anxiety or pain? Panic? Does this patient have a fever? Are they in the acute phases of an asthma attack? Are they compensating for some underlying metabolic problem? Is this provider caused? Did we inadvertently hyperventilate this patient, right? And there are some other things too, but these are some really good things to think about. Now, do we necessarily want to treat respiratory alkalosis?
Treat maybe the causes, like
Okay.
treat for pain, treat for fever.
Okay, so treat the underlying cause, and that may make it go away. But it's really important for us to remember that respiratory alkalosis, right, pain and anxiety, may be indicative of some other problem, right? Like if a big clot forms in my lung, I have a pulmonary embolism, right, and I get that impending sense of doom and death, what am I going to do? I'm going to start breathing, I'm going to hyperventilate, right? There may be some nasty underlying problem going on. And most importantly, if this is compensation for a metabolic acidosis, do we want to treat the respiratory alkalosis?
We want to treat the metabolic.
Good. Absolutely not, right? If this is compensatory, we don't want to treat it, right? We actually want to keep it, right? If you have a patient, say, with DKA, diabetic ketoacidosis, right? Do you want to slow their breathing down? No, you want them to continue to hyperventilate because they're compensating for it, right? If you were to treat the respiratory alkalosis, that would actually harm the patient, right? It would make them more acidotic. Absolutely.
So would you want to induce higher respiratory rate?
Not necessarily. Because generally, if they are awake and oriented in maintaining their airway, they're going to compensate generally with what they need to compensate with, right? So you want to maintain that. Now, what can sometimes happen in diabetic ketoacidosis is they can breathe so fast and so deep for so long that they actually just tire out. They just get tired. They poop out, their respiratory muscles fatigue, and they simply can't breathe like that anymore. And then what happens? Well, we have to breathe for them. But here's the thing. You guys have all been taught, oh, if I ventilate somebody, I need to ventilate them at one breath every 5 to 6 seconds, and then I need to make sure that their end-tidal CO2 is between 35 and 45, right? You guys are probably all taught this. Well, what's that going to do with a DKA patient? That's going to kill them potentially, right? That's going to kill them potentially.
You want to hyperventilate them a little bit?
Yeah, not even a little bit, a lot, right? And so a good thing to do is try to get the baseline. If you suspect that your patient is compensating for an underlying metabolic acidosis, you need to figure out what their baseline CO2 is at, right? And if you need to intubate them or you need to do advanced positive pressure ventilation, hey, prior to intubating this patient, prior to them getting tired, their CO2 was like 20. So what do you need to do? Well, I need to shoot for a CO2 of 20, right? I need to maintain that compensation. Does that make sense? And there are some formulas that I'm going to talk about, not in this class, but in pulmonary medicine. There's something called the Winter's formula. And it's a formula you can actually do that calculates how much you need to compensate. But we don't need to do that here. I want to focus more on the pathophysiology and the problems here when we can talk about treatments in pulmonary medicine. All right, you guys okay with that? Does that kind of make sense? Okay, cool. So that's one of the reasons why, like, if you suspect somebody having a panic attack, back in the day, they used to make them do what? They used to make them rebreathe, right? Rebreathe their CO2 and get their CO2 levels up. But oftentimes, respiratory alkalosis is due to some underlying problem that may be very bad, right? And oftentimes, you know, it may be due to something that we don't want to treat. We want to maintain it. So you need to ask yourself, what is a probable cause, right? And do I need to treat this? Or how do I need to treat it? Okay, so that's respiratory alkalosis. With respiratory alkalosis, some other things that you want to look at is you want to look at how long has this patient been in respiratory alkalosis, right? So if this is uncompensated, all right, that is to say that they do not have a metabolic acidosis, right? This is an uncompensated respiratory alkalosis. That means that this is something that's fairly acute. Does that make sense? That this hasn't been going on for a terribly long time, probably less than a day or so. However, if they are in a compensated, right, this is something that's been going on for more than a day. This is a more of a chronic condition, right? And this is super common here. You guys are probably going to see this when you go to the hospital, when you do ICU rotations, and you're going to have a patient that's been on a ventilator for 3 days. Their blood gas pops out in the morning, and you look at it and you go, oh my gosh, this patient has a respiratory alkalosis, and it looks like their bicarbonate is low. What's going on? Well, they've been hyperventilated for 3 days, and their body is trying to compensate for that. It's really easy to hyperventilate somebody on a ventilator or positive pressure ventilation, and over time they may attempt to compensate for that. You guys okay with that there? Okay, so that's respiratory alkalosis. Let's talk about respiratory acidosis. So respiratory acidosis is really the result of a couple of things. The first thing is it's what? Well, it's not effectively eliminating carbon dioxide. This is often due to hypoventilation, right? A decreased rate and or depth of ventilation. Sometimes, however, this can also be due to what? Making too much CO2, right? If the body is making too much CO2, so more CO2 production than the pulmonary system can handle, right? That can also cause respiratory acidosis. And so, like some conditions we talked about in pharmacology, like malignant hyperthermia, for example. You know, if somebody develops malignant hyperthermia, they may have a normal pulmonary system. They may not have any pulmonary disease at all, but they're making so much CO2 that you just can't blow it off fast enough, right? So these two things can happen. So let's just identify what are maybe some specific common causes of respiratory acidosis.
OD.
Okay, or more generally, let's just say CNS depression. So anything that depresses the central nervous system and suppresses the drive to breathe. So many different kinds of drugs, right? Opioids, ethanol, right? The substantial ethanol overdose, benzos, and so on and so forth. Okay, good. What else might cause CNS depression? Head injuries, yeah. Injuries or trauma. Now, I will also put over here, right, central nervous system issues can also cause respiratory alkalosis, right? There's something called central neurogenic hyperventilation, or somebody has generally like a head injury and they hyperventilate. So head injuries can cause both respiratory alkalosis and acidosis, all right? But yeah, injuries and trauma, particularly trauma that might impact the respiratory muscles, right? If you have trauma that prevents the diaphragm from working or prevents the accessory muscles from working, right? You have, say, paralysis of your intercostal muscles or paralysis of the diaphragm, right? That might be due to injury to the spine, right? The phrenic nerve. You guys probably learned about the phrenic nerve, right? You learned the C3 through 5 keeps the diaphragm alive. Remember that? Yeah, you have a right and left phrenic nerve that goes down the diaphragm. You hit that, and that can impact breathing as well. Yeah. Okay. What are some other things that can cause respiratory acidosis? Obstructive lung disease. Obstructive lung diseases are very good at causing this, right? So obstructive lung diseases are diseases that prevent or make it more difficult for gas to get out of the lungs, right? That's what it means by obstruction. And so COPD, right? COPD, asthma, anaphylaxis may cause this. Obstructive lung disease is really good at causing respiratory acidosis. Central nervous system problems. All right, so I think we have a pretty decent list of things to think about. And could respiratory acidosis also be compensation? There you go. Compensation for a metabolic alkalosis. So that's why it's so important to identify, and remember when we go over the ABGs, every time I ask you, what is the primary problem, right? I say the primary problem is a respiratory acidosis, a metabolic alkalosis, a metabolic acidosis. We identify the primary problem, and then we identify compensation, if it does or does not exist, right? Right? So if your patient has a primary metabolic alkalosis, right, they might develop a respiratory acidosis to compensate, to attempt to compensate for that. Does that make sense? All right. You guys good with that? Hopefully, does that all that stuff make a good amount of sense? All right. Well, it's already been an hour, so let's get you guys on break. When we come back from break, we'll take a deep dive into metabolic problems, and these are a little more difficult to talk about.